Hello students, welcome to this lecture on the logical effort. And in this particular lecture, we will see mostly on circuits, the logical efforts, and then the parasitic, normalized parasitic values, which are estimated for the circuits which are designed, especially for the digital circuits which are designed through the CMOS technology. So let's begin. So it's again an empty slide, which means that I need to summarize some of the concepts. So let's begin with the NAND gate. So I'm going to draw a NAND gate here. And let's say that I'm going to draw the two input NAND gates and then try to find out the logical effort of those two input NAND gates. So in a NAND gate, I will have pull up and pull down circuits where the pull up will be in parallel and pull down circuit will be in series. This will be VDD, and because it's a PMOS, I need to have a bubbled gates in the PMOS side, and then on the NMOS side it will be like this. The sizes is very important here, and as we know, this is a 2 input, so I'll make it the size of 2 and 2 so that the falling resistance will be equal to R, which matches to that of our inverter's falling resistance. On the pull up side, on the PMOS side, I will have the sizes as 2 and 2 so that on a worst case condition, one of the transistors will be on, and then we will have the rising resistance will be nothing but equal to R, which is nothing but equal to that of the inverter's rising resistance. Right, so this is my circuit, and of course this will be my output node. In a linear delay model, we will have the output, the overall capacitance seen at the output node will be nothing but 2 plus 2 plus 2, where this 2 is coming from the NMOS side, and then plus 4 capacitance. So I'm going to write 2C plus 4C. 4C capacitance is coming from the pull up side, or I'm going to write it as PMOS side. So the total is nothing but 6C capacitance, right? But I think what we want is a logical effort. The logical effort, by definition, it says nothing but the ratio of the input capacitance divided by the ratio of the inverter's input capacitance. So what we are saying is here I'm considering the input capacitance for one of the gates. So if I'm considering this as A and A here, so this two will be tied together. And then let me pick another color. So the overall input capacitance here will be nothing but this 2 and then this 2. So it will be nothing but 4C. Right? So this 4C capacitance will be utilized to find out the logical effort for the input A here. I'm just considering the input A at this point of time. You can also have the the logical effort for the B, which will be nothing but in this case it will be nothing but same as the logical effort of A. So the 4C divided by the 3C, right? So 4C divided by 3C. This 3C is coming from that of the inverter's input capacitance, and then this 4C is coming from the two input NAND gates input capacitance. Right, so it turns out that the logical effort is nothing but 4 by 3. And similarly, if I draw the 3 input NAND gate, so let me take another color here. So 3 input NAND gate, I will have 3 of the PMOS transistors in parallel, and then I will have 3 of them in series. So I've drawn this. And this should be bubbled because it's a PMOS transistor, bubbled here, and then I will have all of them NMOS transistors. I'm considering one input because all the other inputs will also see the same capacitance, input capacitance. This is VDD, the other rail is nothing but ground. This is my output node. And let me put the sizes here. For a 3 input NAND gate, we know that the size should be 3 here, 3 here, 3 here, so that I'll get the falling resistance as R, which is similar to that of the inverter's falling resistance. And the sizes should be 2 here, right? So at the input side, I will get, if I connect this to, because it's the same input, so I will have a capacitance The overall capacitance at the input side is nothing but 2 plus 3, which is 5C. So the logical effort by definition, as it says for the input A, is nothing but 5C capacitance seen for this particular gate, and that of the inverter's input capacitance will be 3C, so I'll get 5 by 3. Right here, so what we have done is we have considered the input capacitance of this particular gate, and we took that in the numerator, and in the denominator it is nothing but the inverter's input capacitance. But what it really means is this particular capacitance of 3C and then 5C will ensure, it is actually coming from the sizes of the transistors, right? This 3 transistor is the size, this 2 is the size. The sizes are selected in such a way that I will have the same output current. What do you mean by an output current? So if I draw this particular capacitance here, I will have a total capacitance of 2C plus 2C plus 2C and then 3C here. So I'll get 9C here. In this case, it is nothing but 2C plus 4C, which will give me nothing but 6C. This is the output capacitance. Now, if I'm considering the the falling output, so I'm interested in this particular discharge path, because the Y is going from 1 to 0. That is when we are considering the falling output. The transistor sizes, the size of 3 here is selected in such a way that I will get an equivalent resistance, falling resistance of R, which is similar to that of the inverter's falling resistance. So that is one case. So if I have the switching resistance or the falling resistance as R, I am likely to get a current of I. All right. This current of I, which is nothing but the discharging current of this 9C capacitance, right, which is attributed, which is considered because the falling resistance, the summation of all these 3 switching resistances R, right, is what accounts to this particular current, the discharging current. If I have the same resistance R in a 2:1 inverter, right, if a 2:1 inverter will give me a falling resistance of R, I am likely to get the current of I, even in for an inverter which is falling, which is giving a falling output. That means that the inverter which will see a 3C capacitance at the output will also give me a discharging current of I. Okay. So even for 2:3 size, or for a 3-input NAND gate, 2:3 size means 2 size for the PMOS, 3 size for the NMOS, which will give me, the 9C capacitance. But the 9C capacitance is actually having a discharging current of I, because it sees a falling resistance of R, which matches with that of the 2:1 inverter, which also has a falling resistance of R and a discharging current of I. Right? So in that sense, if I have for both the gates the same current I here, then I can consider taking the ratio, and then that particular ratios giving the same output current. That is what the output current means, the discharging current of the 9C or whatever, 2:1 inverter giving a discharging current of I for a 3C capacitance. So if I have the same currents, right, for the 3-input NAND gates and then for the 2:1 inverter, then I can consider the ratio, and that will be the logical effort, right? So what it really implies is, if I have the width of 2:3, which is more, if I consider this 3 width, right? So the width of 3 is more than the width of 2:1 inverter on the NMOS side. So let me draw the 2:1 inverter somewhere here. So this is the ground, this is the VDD. This is the size of 2, this is the size of 1. I will complete the PMOS. So I will have a bubbled gate, I will have the, the non-bubbled gate representing the NMOS. And this is my output, what I'm saying. So the capacitance at the output is nothing but 3C. Okay. So a size of 1 is giving me a current of I or a resistance of R. So I'm going to write I and then R. Here, for the 3-input NAND gate, For getting the same current I and then for getting the same falling resistance of R, we need to size it, we need to scale it up to 3 times more. So the logical effort here implies that for this particular 3 input NAND gate, I need to have more, more effort when I compare that with that of the inverters. So the more effort means 5 by 3 times more effort is required, so as 5 by 3 times more effort is required so as to get the same current, right? So that's what it represents. So the logical effort by definition says there's an additional effort for the for the 2 input NAND gate or for a 3 input NAND gate, and how much more effort with respect to that inverter will be nothing but based on the input capacitances. All right, so that will be 5 by 3 for a 3 input NAND gate. Similarly, for a 2 input NAND gate, I will have to size it up 2 times more at the NMOS side. So the NMOS side, the inverter is 1, here it is 2, so it is twice more. So my logical effort will be nothing but 4C divided by 3C, right? 4 by 3. What it also says is the logical effort for a 3 input NAND gate is more than the logical effort of the 2 input NAND gate. And it is quite obvious, 3 input NAND gates will, I'll need to size it up 3 times here. And for a 2 input NAND gate, I need to size it 2 times. So its input capacitance will be 4C. Here the input capacitance is 5C. All right, hope this is clear. Kind of very important at this particular point of time when we are designing the gate sizes. Okay. So again, an empty slide. So I need to summarize for the NOR gates. So let me quickly draw the NOR gate, 2 input NOR gate. Again, a 2 input NOR gate, I will have on the PMOS side, I will have a series of 2 PMOS transistors, and then on the NMOS side, I will have it parallel. So this is my NMOS and this is my output. This is VDD and this will be my PMOS transistor. The sizing of this particular PMOS transistor is done such that I will have equal falling and equal rising resistance to that of the inverters, 2:1 circuit. So here I will size it to 4 and 4 so that I will get R by 2 from this individual PMOS transistors, and put together I will get an rising resistance of R. Here I will make it 1 and 1. So my logical effort, if I consider one of these inputs which are tied, if I consider this to be an A input, this to be an A input, I will get, the capacitance of 5C here. So the logical effort will be for the input A here will be nothing but 5C divided by the inverters, 2:1 inverter here. So I'm going to draw that VDD rail and then 1 and then the ground rail and then size of 2:1, which will give me an output here Y. So if I consider the capacitance here, it will be nothing but 3C here, which will have the current of I and then the resistance of R. Similarly, if I consider the output capacitance here, which will be nothing but 1 plus 1 plus 4, which will be 6C here. And then this one, while it is falling, I will get a current of I and the resistance of R. And while it is charging, so it will have a current of I and then the rising resistance of R. So similarly for the charging for this 3C, I will have a current of I and then the rising resistance of R. So it matches both the benchmark inverter of 2:1 matches with that of our 4:1, which is nothing but 2 input NOR gate. And then I can take the ratio of 5C and then the 3C. So eventually I will get the logical effort for a 2 input NOR gate is 5 by 3. And similarly, just to complete, we will draw a 4 input NOR gate. So I'll skip the 3 input NOR gates because we have anyways done the 3 input NAND gate. So the 4 input NOR gate, I will have 4 transistors in series on the pull up side and then 4 of them in parallel on the pull down side. So I'm just going to draw this transistors, complete it. And then I will have this 4 of the series transistors complete the VDD rails, and then anyways we have the ground. So this will be my output Y. Putting the sizes now. So this is 4 of them. So I will have it as an 8 here, size of 8 here, size of 8 here, which will give me an equivalent of R by 4, R by 4, R by 4, and R by 4 for the individual transistors, and then put together it will be a rising resistance of 1 R, which will be equal to that of the benchmark inverter 2:1 ratio inverter rising resistance. And on the pull down side, I will have a size of 1, and 1, so that I'll get, in the worst case condition, one of them will be on, and then I should be able to get the output discharge to 0. And that is where that's why I have the size of 1 here. The output capacitance, just for our own understanding, I will have to have some capacitance, which will be nothing but 8 plus 1 plus 1 plus 1 plus 1, which will be nothing but 12C. So the output capacitance, while it is discharging, it will be discharging with a current of I, and then the falling resistance of R. And while it is charging, so it will have a rising resistance of R, and then the current, charging current, will be nothing but I. Right. So in that sense, the logical effort in this case will be nothing but logical effort of one of the inputs. I'm considering it as an A input. So it will be nothing but 8 plus 1, which will be 9. 9C by 3C. 3C is coming from the benchmark inverter of 2:1. So I will get the 9 by 3. Right. So this is for the 4 input NOR gates. Right. Of course, 9 by 3 will become nothing but 3 by 1. Hope this is clear. So moving ahead. So what I've done is I've summarized it for the 2 input NAND gates, 2 and 3 input NAND gates, the delay, and the 2 input NOR gates, and then 3 input NOR gates. And finally, we have evaluated for the N input NOR gates and then the N input NAND gates. Right. So let's quickly take a look at it. So this is the delay values. So 2 input NAND gates, I'm saying that the delay is nothing but 2 plus 4 by 3 into H. Okay, let's not worry about this 2. Let's come to that later. So 4 by 3, that is what we had seen in the last couple of slides, 4 by 3 for the 2 input NAND gates. For the 3 input NAND gates, we will have 5 by 3. For the 2 input NOR gates, we had seen 5 by 3, and then for the 4 input NOR gates, we had seen 9 by 3. For the 3 input NOR gates, it will be 7 by 3. So the logical effort turns out to be 4 by 3, which is nothing but coming from the 4C as the input, the input gate capacitance of the gate, divided by the 3C coming from the 2:1 inverter. And for the 3 input NAND gate, again, we had seen 5C and then divided by 3C. For the 2 input NOR gate, it is 5C by 3C, and then for the 4 input NOR gate, it is nothing but 9C divided by 3C. For the 3 input NOR gate, it is nothing but 7C divided by 3C. So if I put together, if I want a generic expression for an N input NAND gate, so if I look into this aspect, right, 4C and then 5C. So this 4C is actually coming from 2C from the NMOS side, and then NMOS, which is in series with the other NMOS, and then this 2C coming from the PMOS side. This 5C, if I consider, it is actually 3C coming from the NMOS side. So I'm going to write it as N, and then this is P. So I'm going to write it as N, and then this is going to be the 2C coming from the PMOS side. So if I similarly calculate the logical effort of a 4 input NAND gate, so the 4 input NAND gate, it will be nothing but, so I'm going to write it as 4 NAND, and then the logical effort, it will be nothing but, so I have to size it accordingly. So I'll have to have 4 times the width, right? And then this will come from NMOS, which is at the output node, the NMOS transistor, which is very close to the output node, plus plus the 2C coming from the PMOS input. So 4C plus 2C, that is coming from the PMOS. So the overall, what I'm saying is, as the number of inputs increases for the NAND gate, for the 2 input it is 2C, for the 3 input it is 3C, for the 4 input it is 4C, for the N inputs it will be NC on the NMOS side, plus 2C from the PMOS side. So that's what I have here. So to generalize it, it will be nothing but n, for the n input, it will be n plus 2 divided by the 3, which is coming from the inverters 2:1, which is nothing but the benchmark inverter, right? Giving the same output current. So n plus 2 divided by 3. So that becomes our general expression for finding the logical effort for an n input NAND gate. So similarly, if I want to find out the logical effort for an n input NOR gate, so if I pick this 5 by 3, the 5 by 3 is actually coming from 4 capacitance, the width of the 2 input NOR gate, especially on the PMOS transistor, is 4, right? The width is 4, so its input side, the capacitance will be 4C, and 1C coming from the NMOS side. This 7 by 3, this particular 7 is actually coming from, for a 3 input NOR gate, the width will be 6, so 6C on the input, on the PMOS transistors input gate capacitance, plus 1C coming from the NMOS width will be 1, so its input gate capacitance will be 1C. For the 4 input NOR gate, it is actually 9C, which is actually coming from 8C, because the width is 8, so its input capacitance will be 8 on the PMOS transistor, and its the subsequent NMOS transistor will have a capacitance of 1C because the width will be 1, so that's how it will be 9C. So if I look closely into it, for a 3 input it is actually 6C, for a 2 input NOR gate it is actually 4C. So for an n input NOR gate, it turns out to be 2n coming from the PMOS side, and this 1 is coming from the NMOS side, and then divided by 3. The 3 is nothing but coming from the benchmark inverters 2:1 inverter. So hope this is clear. So the logical effort, general expression for a NOR gate and NAND gate is nothing but 2n plus 1 divided by 3 and n plus 2 divided by 3. Right? Kind of very, very important when we try to estimate the overall delay for a critical path of a large digital circuit. And in this particular critical path, we have, let's say that, you have, you will observe a lot of NAND and NOR gates of different inputs. Then I think using the linear delay model, we need to estimate what is the logical effort. And then this particular generic expression will be very, very handy to use in those larger circuits critical path. Right? Moving ahead. So now I think, the logical effort is done. And the other component is the normalized parasitic delay. So again, I've taken an example here of the 2 input NAND gates. Again, the 2 input NAND gates, so as to get the equal falling and a rising resistance as that of the 2:1 inverter here. So we will see a capacitance of 6C here coming from 2 on the NMOS side and then 2 and 2 on the PMOS side. So this 6C capacitance has arrived from 2C on the NMOS side, right? Plus there are 2 parallel legs, or there are 2 PMOS transistors which are parallel. So I will get 2C into 2, right? And the parasitic, normalized parasitic, the definition still remains the same. It is nothing but the ratio of, it is a normalized parasitic delay is nothing but the ratio of the capacitance of the gate, which we are calculating the normalized parasitic delay with respect to the capacitance of the inverter. Now, what are these capacitances? These are nothing but the capacitances which are seen at the output node. So whatever we see, the overall or the effective capacitance seen at the output node, so that we have to consider in the numerator side for calculating or evaluating the normalized parasitic delay, divided by the capacitors of the inverter. Right, in a 2:1 inverter, I will see a parasitic capacitance of 3C. So that is what the capacitance seen at the output node. So 3C will come here, and it is giving the same output current. Right, so the definition of the logical effort and the definition of normalized parasitic delay remains the same in that perspective, because we need to compare compare the output node capacitance in this particular case, where the output node capacitance actually discharges, right, having the same current, having the same output current, right, while it is falling, and while it is rising, it should have the same uh, rising current of I, which is same as that of the inverter's rising current of I. So I'm going to write it I. So if I have the same rising current, what it means is the rising resistance is nothing but R, and of course the falling resistance will be nothing but R, and then this will be I comma R. So that's what the definition is. So once I have the same output current, then I can actually do the ratio of the capacitance seen at the output node for that particular gate, and with respect to that of the capacitance at the output node for the benchmark inverter 2:1. Right. So in this particular case, if I take a standalone 2-input NAND gate, I will see a 6C capacitance divided by 3C, which will be nothing but 2. Right. So again, for a parasitic normalized parasitic delay for the 3-input NAND gate, 3-input NAND gate will be nothing but so I will have a size of 3 here on the pull down circuit. So I will have a 3C capacitance connected to the output node, plus this one will remain the same. So I will have 2C, 2C, and then 2C coming from the another third transistor. So I will have 2C multiplied by 3 divided by the 3C, the inverter's capacitance. So it turns out to be nothing but 3. All right. So moving ahead, so just to generalize this, for a 3-input NAND gate, this is what we have the sizes in the schematic. So the output node capacitance is 9C. So the parasitic delay is nothing but, for a 3-input NAND gate, is nothing but this 9C taken into the numerator, and then this 3C coming from the inverters, the benchmark inverters 2:1 ratio inverter, giving an output capacitance of 3C, and both of them is giving the same current, output current. So I will have, so in general, if I want to find out the parasitic delay for an n-input NAND gate, this sizes for an n-input NAND gate will be nothing but n. Okay, and this sizes will remain to be 2, because for a NAND gate, the worst case is one of the transistors on the pull-up side will be on, and then that is how the output will reach to a logic 1. So I will have, if suppose I have this n such transistors, so this on the PMOS side, the n such transistors are going to contribute to 2C capacitance multiplied by n times. So it will be 2n times the capacitance. And then this n is coming from the transistor which is closest to the output. Right? So this NC will be incorporated into the output capacitance seen at the output node Y. So I will have n plus 2n C divided by 3C. So it will be n plus 2n divided by 3. So it will be nothing but n. So for an n input NAND gate, the parasitic delay is n. The logical effort is nothing but n plus 2 divided by 3. All right, hope that is clear. For a, I have drawn a 3-input NAND gate and then generalized for an n-input NOR gate, what should be the parasitic delay. So for a 3-input NOR gate, we need a size of 6 here, 6 here, and 6 here. So this 6C is going to contribute to 6 times the capacitance at the output node. And on the pull down side, we have the sizing as 1, 1, and 1. So that in worst case, I will have the falling resistance of 1R, which will give me a output current of I, 1I. So all these transistors 1C, 1C, and 1C individually will contribute to 1C, 1C, and 1C at the output side. So overall, I will have a 9C capacitance. Right, so 6 coming from the PMOS side, and then this PMOS side, and then 3 coming from the NMOS side, divided by 3C. So this 6 is actually coming from twice the number of input, so the 3 input, plus this 3 is coming from 3 into 3 transistors multiplied by the size as 1. Right, so in that sense, and then divided by 3C from the inverter, 2:1 benchmark inverter. So if I consider that, So this 2n is coming from the PMOS side. For an n input NOR gate, I will have 2 times n for the PMOS transistor which is closest to the output node. So this one will give me, for an n input NOR gate, I will have to have 2 times the n size, and so that will contribute to 2n C capacitance at the output node. And on the NMOS side, each of this NMOS is going to contribute towards 1 C capacitance. So the n such parallel transistors on the NMOS side is going to contribute n C capacitance. And of course, divided by 3C will give me, 3n divided by 3 will give me an output of n. So the parasitic delay for a 3 input NOR gate is still n. Or rather, for a 3 input NOR gate, it is 3. For an n input NOR gate, it is n. Parasitic delay for a n input NAND gate is also n, right? Whereas the logical effort for a n input NOR gate turns out to be 2n plus 1 divided by 3, which will always be larger than the logical effort for an n input NAND gate, right? So in that sense, the parasitic delay, although the parasitic delay of the NOR and the NAND gates are same, the logical effort for the n input NOR gate will always be larger than that of the n input NAND gate. So a NAND gate is always preferable in designing the digital circuits. Hope this is clear. Okay, so this is what I have summarized. So for the n input NAND gate, and then for the n input okay, this should be NOR. So for n input NOR gate, it is n, right? The overall delay is nothing but the parasitic plus G into H. So 2 plus, again, it's a normalized delay. So for a 2 input NAND gate, it will be 2 plus 4 by 3 into H. For a 3 input NAND gate, it will be 3 plus 5 by 3 into H. And for a NOR gate, 2 input NOR gate, it will be 2 plus 5 by 3 into H. The logical effort of a NOR is 5 by 3. And then for a 3 input NOR gate, it is 7 by 3 into H. So overall, the overall delay for the n input NOR gate will be nothing but n normalized 1 plus 2n plus 1 divided by 3 into H. And if I want an absolute value of the delay, it will be nothing but this. I have to multiply by 3RC, right? Because we have always taken a ratio while we are calculating the normalized delay. We have taken a ratio with respect to the benchmark inverter's delay, which is nothing but 3RC. All right. And similarly, for the delay for an n input NAND gate will be nothing but n parasitic delay plus n plus 2 divided by 3 into H. Again, this will be the normalized delay.